You are looking at the screen of a Dorado personal workstation running the Cedar programming environment. On the screen is a Gargoyle3D editing window containing a model of some blocks. The square that is moving on the screen is a hardware cursor controlled by my mouse. When I hold down a special combination of keys, a software cursor, called the skidder, follows the motion of the cursor, snapping to objects that are under the cursor. If there are no objects under the cursor, the skidder moves around on a default plane parallel to the screen. Currently, I'm using the Faces Preferred gravity function. With this gravity function, the skidder snaps to the nearest surface that is under the cursor. White squares appear on the vertices and the centroid of the block where the skidder lands, so I will know when the skidder is on the right block. Notice that the z-axis of the skidder, drawn as a narrow triangle, stays perpendicular to the faces of the cubes, giving us another clue as to which face we are on. If I wish the skidder to snap to hidden features, I can use another gravity function. For instance, with points preferred gravity, I can snap to visible edges, to visible vertices, or to hidden edges and hidden vertices. Notice that the x-axis of the cursor aligns itself with an edge when the skidder snaps to an edge, and to one of the possible edges that meet at a vertex when the skidder snaps to a vertex. Later, we will use the x-axis of the skidder as an axis of rotation. By holding down a different set of keys, I can select objects. Black squares appear on the vertices of the blocks that would be selected if I stopped now. I can also select parts of objects, such as faces, edges, or vertices. Notice that when I select a part of a block, its unselected vertices highlight with white squares. This helps me decide if I'm selecting the correct part of the correct object. For instance, right now I'm selecting a vertex, but which of the three cubes does it belong to? The white squares tell me that it is this one. Now I'll select a block and translate it. During translation, the selected objects follow the skidder, and the skidder continues to snap to objects as before. Thus, I can drag my cube along the default plane and snap it to faces, edges, and vertices. Similarly, when I stretch an edge into the scene, I can rubber band it, snapping it to the default plane or to object features using any of the three gravity functions. In addition to faces preferred and points preferred gravity, I have lines preferred gravity. This third gravity function helps the skidder snap to edges and faces, but doesn't treat vertices specially. I can use this gravity function to place the skidder on an edge near a vertex without snapping to the vertex. In this scene, I will demonstrate translation, rotation, and scaling by using them to place a tetrahedron on one face of an octahedron. First, I place the skidder on the tetrahedron, which has been selected. Next, I begin a translation operation. The tetrahedron follows the skidder, moving on the default plane, until I snap the skidder to one of the vertices of the octahedron. Next, I would like to rotate the tetrahedron so that this edge is coincident with this edge of the octahedron. First, I click a button which places a special shape called the anchor at the point that the tetrahedron and the octahedron share. I will use the anchor as a center of rotation. I place the skidder on the other end of the edge that I'm going to rotate, and I rotate the tetrahedron around the center of the anchor until its edge snaps to the edge of the octahedron. Next, I'm going to scale the tetrahedron up until its edge is the same length as the edge of the octahedron. I place the skidder on the end of the edge I'm going to scale and begin the scaling operation. When I snap the skidder to the vertex of the octahedron, the two edges are now the same length. Finally, I'm going to rotate the tetrahedron so its face becomes coincident with this face of the octahedron. To do this, I need to rotate around this axis. Fortunately, because the x-axis of the skidder aligned with the edge of the octahedron before I placed the anchor, and because the anchor takes its orientation from the orientation of the skidder, its x-axis is already aligned with this edge. Hence, my operation, which rotates around the x-axis of the anchor, is exactly what we need. I perform the rotation, and finally, when I snap the skidder to the vertex of the octahedron, the tetrahedron is precisely aligned with the face of the octahedron. To perform precise constructions in Gargoyle3D, we can take advantage of alignment objects. For instance, to place a copy of this cube directly in front of it, I might begin by making some of its points hot. Hot points are shown as large white squares. Then I will activate alignment lines of azimuth 90 degrees and slope 0 degrees. One line is constructed at each of the vertices that I made hot. These alignment lines run in and out of the screen parallel to some of the cube's edges. When I snap the skidder to one of these lines, it darkens, and starbursts appear at all of the hot vertices that trigger that line to give me confidence that I'm snapping to the correct line. I will copy the cube, taking advantage of the alignment lines to place the copy precisely. Now, I will activate a second set of alignment lines at azimuth 0 degrees and slope 0 degrees, and make more vertices hot. These new lines will help me place a second copy. If I make more vertices hot, more lines are generated. When I snap the skidder to an intersection point of two lines, starbursts appear on all four of the vertices that trigger either of the two intersecting lines. Using the intersection point, I can place one last copy of the cube aligned with the others. Now I would like to copy all of these cubes so they will be directly above the originals. I turn on slope lines of azimuth 0 and slope 90 degrees, place my skidder on one of the cubes, and copy all of them up. Now I will get rid of the alignment lines. I'm going to use alignment lines and alignment spheres to construct a regular tetrahedron. First, I place the skidder on the default plane and rubber band a line snapping its new end to the default plane as well. Next, I make one end of the line hot and turn on alignment lines of azimuth 10 degrees, slope 0 degrees. This will give us a tetrahedron in a nice orientation. I can grab the other end of the line segment and snap it on to this alignment line, so now it is at azimuth 10 degrees and slope 0 degrees as well. Next, I'm going to turn on an alignment sphere of radius 4 inches. The sphere draws itself as just a silhouette circle. However, it really is a three-dimensional sphere. As I move the skidder around on the surface of the sphere, notice that the z-axis of the skidder changes its direction to correspond to the surface normal of the sphere. I can also snap the skidder to the intersection point of the sphere with the alignment line, giving me a line segment of length 4 inches at a known orientation. Next, I'm going to make the other end of the line segment hot. Now both ends of the line segment are triggering alignment spheres, and Gargoyle3D automatically computes the intersection circle of the two spheres. I'm going to rubber band a new line segment into the picture, snapping its endpoint to the intersection circle of the two alignment spheres. Finally, I will add a third line segment. I've now constructed a regular equilateral triangle in 3 dimensions. Next, I'm going to make the third vertex of this equilateral triangle hot. Now there are 3 alignment spheres being triggered. And Gargoyle has computed the pairwise intersections of all of them. In particular, up here and down here are points where all 3 alignment spheres meet at a point. If I add a 4th line segment to that triple point of intersection, I now have all of the vertices of a regular tetrahedron. I will finish the tetrahedron by adding 2 more line segments. Next, I'll move the tetrahedron down and make copies of it to build a tetrahedron made of 4 tetrahedra. Next, I would like to show you alignment planes. I have placed the anchor on the default plane, and now I will turn on an alignment plane whose surface normal has azimuth 0 degrees and slope 90 degrees. In other words, it's a horizontal alignment plane. When I begin to move the skidder, it now moves around on the alignment plane. And the parallelogram, which represents the alignment plane on the screen, darkens to show that the skidder is moving on it. Let me turn on a second alignment plane, this one making a sort of a back wall of a room that we're facing. Now when I move the skidder around, it moves on the horizontal plane in this region and the vertical plane in this region, because in this region the vertical plane is closer to us than the horizontal plane. When I snap the skidder to the intersection line of the 2 planes, both planes light up to remind me that I'm on a line that was caused by both of them. Finally, I'm going to turn on one last alignment plane, this one forming sort of a left wall of the space that I'm moving around in. Again, as I move the skidder around in this region, I move on all 3 planes, here the left wall, here the floor, and here the back wall. And as I snap to intersection lines, the planes highlight in pairs. Now I'm going to play a script that uses alignment planes and alignment spheres to construct a regular octahedron. The script places the anchor, turns on the alignment spheres and 3 alignment planes, and then snaps the skidder to intersection points of the circles made by the intersection of the alignment planes with the alignment sphere. And finally, it just finishes up the octahedron. 3-dimensional snap-dragging works well with objects, some constraints placed upon them. For instance, all of the block objects that we have been seeing are constrained to remain in block shape. This is useful when a part of the object is selected and translated. For instance, here I select the edge of one of the blocks and begin to translate it. Because the block is constrained to stay a block, I can only change 2 degrees of freedom. The length of the selected edge in particular stays the same. When I snap the skidder to this vertex here, I've aligned the mattress of a 4-poster bed with the 4 posts. Similarly, if I select just one face of one or more blocks and translate them, for instance by moving the skidder around on the default plane, then only one dimension, the height of each of the blocks, changes as I move.